be a specificity in domain.
Thank you very much. Thank you very much.
Great. The next talk is by Stefania Mattioni, Institute of Research in Psychology, Louvain, Belgium. How input modality in visual experience affect the neural encoding of categorical knowledge.
Thank you. Visual categorization is something that we use in our everyday life to organize the massive amount of visual information that we receive from our environment. The main distinction that we find is the one between animate and inanimate. And then normally we also create some subclusters within these two big categories. But what is the neural substrate for this process? It has been shown to be the ventral occipitotemporal cortex. And in fact, we find some regions, some clusters of voxel inside this area that show a preferential response to one of these categories when compared to the others. However, what still we don't know is actually what drives the development of this categorical organization. So what makes one region to develop a preference for stimuli such as faces or for stimuli such as houses? Actually, there have been many suggestions, starting from low-level visual characteristic of the stimuli such as retinotopic eccentricity or rectilinearity, or some more middle-level visual properties such as the real-world size, or even some more high-level characteristic of these stimuli, for example, to be animated or not, and even the category membership itself, so being a face and a house. Actually, to test this last hypothesis is not easy. In fact, it's quite difficult to segregate the category membership from the other low and middle visual level visual characteristic that all the stimuli share within the same category. We thought that a good solution would be to use auditory category, so category presented in the auditory format, and even more, to present them to a group of people that are born blind. In fact, we thought that if we can find a similar categorical organization inside the OTC, also in people that have no visual experience at all, this would be a definitive proof that this region does not need visual experience to develop its categorical organization. So we included in our study 3 groups, one of sighted people that did a visual experiment, one of blind that did an auditory experiment, and an additional group of sighted that did also the auditory experiment as the blind. I presented 8 different categories derived hierarchically from the 2 animate and inanimate categories. And I showed these 8 different categories to my participant in the fMRI, using a fast event relate design that was the same in the 2 versions, the visual and the auditory one. And the participant had to do a one-back task. So then I extracted 2 regions of interest in the subject space of my participant. So one more posterior, the early visual cortex, known to process the low-level features of visual stimuli, and then the ventral occipitotemporal cortex. I performed pairwise decoding in these, for my 8 categories in these 2 regions. So for each pair of category, I extracted the decoding accuracy. So this means that with 8 categories, I did that for 28 possible pairwise. So I will start to show the results from the average of these 28 values in each group, in each region of interest. So as expected in both early visual cortex and the OTC, we find that they can easily classify the category when they are presented visually in sighted. What is more interesting to see are the results from the auditory experiment. So in here, as you can see, in the blinds that are in orange, also early visual cortex and VOTC can decode the different categories better than the chance level and also significantly better than the sighted group. However, it is important to notice that the VOTC is actually decoding the different categories significantly better than chance, also in the cited. So what these data are suggesting is that VOTC keep information about different categories when they are presented visually in cited, but also when they are presented in the auditory format in both blind and cited. So now something interesting would be to understand if VOTC functional profile is actually similar in these three groups. So first of all, what do I mean with functional profile? If we look at the 28 different pairwise, we see that in each group there are some categories that are represented more similarly in the brain, so they trigger low decoding accuracy, and others that are represented more differently in the brain, and they trigger high decoding accuracy. So if we now look at throughout the 28 pairs that I have, we can see a sort of functional profile that we can also represent in the format of a symmetrical dissimilarity matrix. And what would be interesting now is to understand if the same categories that are represented similarly in the VOTC of one group would be also represented similarly in the VOTC of the other groups. And to do that, we computed a correlation between these functional profiles. And here are the results plotted. And we see two important things. The first one is that the functional profile of VOTC is between sighted in vision and early blind in audition share the highest similarity compared to the other pairwise. But we also see that all the correlations are actually significant. So this means that the VOTC functional profile shares similarities across the three groups. So at this point, the next piece that we need to understand is if the same features of the stimuli are actually driving this functional profile. So there would be something completely similar, the same features such as high-level categorical membership in the three groups, or it would be some more low-level properties of the stimuli, so more visual properties in the visual experiment and auditory properties of the sound in the auditory experiment. To address this question, we created some models based on our stimuli space. So some high-level models based on the behavioral rating of our participants, or some low-level models based either on the visual properties of the stimuli in the visual experiment, so the HMAX model, or the pitch model for the auditory stimuli. And then I correlate them with the brain models to understand which of these models better explain the functional profile of VOTC in the three groups. And here are the results. So in the visual experiment, we found that in the early visual cortex, the HMAX model is the one that more explains the functional profile of this region, that is in the light gray. While in the VOTC, it's the behavioral model that is now explaining more the functional profile of this region. But this was quite expected. While if we go in the auditory experiment, we see that in the early visual cortex, none of the models can explain the functional profile of this region. But in VOTC, we now see that the behavioral model is actually explaining significantly the functional profile of VOTC in both early blind, in dark orange, and in sighted also, in dark blue. So we see here that actually the categorical membership of this stimuli is significantly explaining the functional profile of VOTC in the three groups. So it's time now to have a summary of what I show you. So we saw that the functional profile, the categorical organization that we see in for the visual stimuli in sighted, it's actually partially preserved also for the auditory stimuli, and it's even enhanced in the case of early visual deprivation. I show also that these functional profiles share similarity across the three groups, and that they are explained by more high-level categorical membership of the stimuli and not by the physical properties of the stimuli. So we can conclude that the categorical organization of VOTC can develop also without visual experience, and that can be considered at least partially abstracted from the visual input. And with this, I want to thank my PI, Olivier Collignon, my group, and thank you for your attention.
We have time for questions.
Hi. Maybe I missed this, but I was wondering, what was your behavior?
Sorry, the participant?
What was the behavioral model? Like, what behavior was it based on?
The behavioral model was based on the rating of the participants. So they had to judge how similar were the stimuli. And in the visual experiments, I presented the stimuli visually also in this part. And in the auditory experiment, it was auditory stimuli. And actually, as you can see here, they are actually very correlated in the three groups. And they are also very correlated with the categorical model. Here. So they are actually very correlated and also they basically based their behavioral ratings on the categories. All the animals were clustered together and all the...
One more question?
Yes.
Okay.
Hi, thank you.
Hi.
One question. Obviously, you managed to decode the categories, right? I mean, with the decoding analysis. But does the spatial profile look similar? I mean, does the activation in the visual cortex, for sound in the blind subject look like you get it in the visually normal condition?
You mean at the univariate
yes.
analysis?
I mean, do you see the same spatial specificity?
Yeah,
or,
actually...
I mean, you say this actually corresponds, but you can decode, right? That's
yeah,
not the same
sure. Sorry, I have many. So yes, actually, yes, it's here. We see that if I use a winner-take-all approach, and here I plotted like the selectivity maps for these 4 categories. So we see that actually we find a sort of similarity also at the topographical map, and it's quite high. It's a correlation of 34. So it's especially related to the big manipulable and humans, and the animals is less represented in the blind, but yes.
Okay, thank you.
You're welcome.